In everyday experience, time appears to have three distinct properties. It seems to move, carrying events from the future into the present and then into the past. It seems to have a single present moment, a now that everyone shares. And it seems to run in one direction only, never backward. These three assumptions feel self-evident. They organize how we plan, remember, and speak. Modern physics supports almost none of them. Beginning with Albert Einstein's theory of special relativity, published in 1905, the equations that describe motion, space, and time contain no term for flow. Nothing in them singles out a present moment. Nothing distinguishes past from future in the way our experience insists we must. When physicists write down the fundamental laws, time enters as a coordinate, similar in form to the three coordinates of space, and the universe is treated as a fixed geometric structure rather than a sequence of unfolding events. This structure has a name. It is called the block universe, and the reasoning behind it is not speculative in origin. It follows from relativity, one of the most precisely tested theories in the history of science, confirmed by particle accelerators, atomic clocks flown on aircraft, and the satellites that make navigation possible. If those experiments are correct, and they have never failed, then the flowing time we take for granted may not exist in the physical world at all. The question this raises is direct. If the equations describe a universe where every moment already exists, why do we experience time as passing at all? The clearest way to understand why physicists doubt that time flows is to begin with the theory that first made the doubt unavoidable, and to see exactly what it replaced. Before Einstein, the dominant description of time came from Isaac Newton, and it matched intuition almost perfectly. Newton wrote in the late 1600s that time was absolute, true, and mathematical, flowing equably without relation to anything external. Stripped of the period language, the claim was simple. Somewhere behind the visible universe there ran a single master clock, ticking at one fixed rate, setting the pace for everything at once. A second on Earth was a second on the moon, a second in a galaxy no telescope could reach, a second everywhere without exception. Two events that occurred together were together for all observers, regardless of where they stood or how they moved. Duration was a property of the universe itself, not of any particular observer within it. This was not merely one man's philosophy. It became the unspoken foundation of all physics for roughly 2 centuries, and its record was extraordinary. Working within Newton's framework, astronomers predicted the return of comets to the week. Engineers built machines of increasing complexity. The motion of the planets was charted, the tides explained, the path of a projectile calculated in advance with reliable accuracy. When a new planet, Neptune, was discovered in 1846, it was found because Newton's laws had predicted the location of an unseen mass from the wobble it produced in the orbit of another. A framework that could reveal a planet no one had ever seen did not invite doubt. The absolute clock seemed as secure as any idea in science. The trouble arrived from a direction no one was watching, not from the study of time, but from the study of light. Across the 1800s, physicists established through careful experiment that light behaved as a wave, and that it traveled at a definite speed, close to 300,000 kilometers in every second. That figure, once measured, raised an immediate and reasonable question. Waves, as everyone understood them, were disturbances in some medium. Sound is a disturbance traveling through air, and where there is no air, there is no sound. Ocean waves are the motion of water, meaningless without the water. If light was a wave, it too should require a medium to carry it, and physicists gave that hypothetical medium a name, the luminiferous ether, imagined as an invisible substance filling all of space, the still backdrop through which light rippled. The ether offered something Newton would have welcomed. If it filled space and stood at rest, it defined a state of absolute rest, a fixed stage against which all motion could be measured. And it suggested a test. The Earth moves through space as it orbits the Sun at about 30 kilometers per second. If the planet plows through a stationary ether, then a beam of light sent in the direction of that motion should travel at a slightly different measured speed than a beam sent across it. in the same way that a swimmer's progress depends on whether they move with a current or against it. The difference would be tiny, but by the 1880s, instruments had become sensitive enough to catch it. The decisive attempt was carried out by Albert Michelson and Edward Morley in 1887. Their apparatus split a single beam of light into two, sent the halves along paths at right angles to each other, then recombined them. If the two halves traveled at even slightly different speeds because of the Earth's motion through the ether, they would fall out of step, and the recombined light would show a distinctive pattern of interference. The device was mounted on a heavy stone slab floated in a pool of mercury so it could be rotated smoothly, allowing the arms to be swung into every orientation relative to the Earth's motion. The experiment was among the most careful ever performed. It was capable of detecting a shift far smaller than the one predicted. It detected nothing. Light traveled at precisely the same speed in every direction, at every orientation, at every point in the Earth's orbit. There was no sign of the ether, no variation, no current to swim against. Under the reigning framework, this was close to impossible. Everyday experience with velocities is unambiguous. Run toward an approaching object and it closes on you faster. Move away and it approaches more slowly. Speeds add and subtract. Light refused. Whether the measurement was taken along the Earth's motion or across it, toward a source or away from one, the beam arrived at the same unchanging speed. Something in the deepest assumptions had gone wrong. For nearly 2 decades, physicists tried to preserve the ether by amending it. The most ingenious proposal held that objects physically shrank in the direction of their motion by exactly the amount needed to hide the effect, so that the measuring apparatus itself contracted and concealed the difference it was built to find. Others suggested the Earth dragged a layer of ether along with it, so that near the surface there was no relative motion to measure. Each fix accounted for the null result, and each demanded a new and unexplained mechanism to prop up the previous one. The structure grew heavier and less believable with every addition. The ideas were not disproven so much as exhausted. Einstein, in 1905, took a different route. Rather than asking what could be added to save the old picture, he asked what the universe would have to be like for the Michelson-Morley result to be exactly what one should expect, requiring no rescue at all. He proposed that the constancy of light speed was not a puzzle demanding explanation, but a fundamental law, a fixed and irreducible feature of the world. To this he joined a second principle, equally plain in appearance, that the laws of physics take the same form for every observer, moving at a constant velocity, with no observer occupying a privileged position from which reality looks different. Neither principle sounds threatening. The first says light has a set speed. The second says the rules do not change depending on your steady motion. Placed side by side, they force a conclusion that removes Newton's master clock entirely. The reasoning turns on what speed actually is. A speed is a distance divided by a duration, a length measured against a stretch of time. Suppose 2 observers move relative to each other, and both measure the same pulse of light. Both, by the first principle, obtain the identical speed. Yet they are in motion with respect to one another. The only way both can measure the same ratio of distance to time while moving differently is for their measurements of distance and of time to differ. One observer's meter and one observer's second cannot equal the other's. To hold the speed of light fixed for everyone, space and time themselves must yield, stretching for one observer and compressing for another, adjusting so the ratio always comes out the same. The rigidity Newton assigned to length and duration was the very thing that had to be given up. Space and time became elastic, and the quantity that stayed rigid instead was the speed of light. From this shift, 2 effects follow with mathematical necessity, and both have since been confirmed to remarkable precision. The first is that a moving clock runs slow, judged by an observer it passes. Not because motion jars the mechanism or damages the gears, but because time itself, for the moving object, elapses at a reduced rate. At the speeds of ordinary life, the slowing is so slight it escaped every observer for centuries. A passenger jet crossing a continent for hours falls behind a ground clock by only a handful of billionths of a second, But as an object's speed climbs toward that of light, the effect grows without limit, and near that boundary time slows almost to a standstill. The demonstration is not confined to instruments. Particles called muons, produced when cosmic rays strike the upper atmosphere, provide a continuous natural test. A muon at rest survives for about 2/millionths of a second before decaying. Traveling near light speed, it should manage only a few hundred meters before it disappears, far short of the roughly 15 kilometers between where it forms and the ground. By that arithmetic, almost none should reach the surface, yet detectors register them arriving in abundance every second of every day. They complete the journey because, at their speed, their internal clocks run so slowly that a span which should have been a fraction of a microsecond is stretched into ample time. The particles do not cheat decay. Their time simply passes more slowly than ours, in exact agreement with the equations. The second effect mirrors the first but applies to space. An object in motion is measured shorter along its direction of travel than the same object at rest. The contraction, like the slowing of the clock, is undetectable at familiar speeds and pronounced near the speed of light. Distance itself, the separation between one point and another, depends on the motion of whoever measures it. Both predictions have been checked repeatedly and have never failed. Atomic clocks, precise to within billionths of a second, have been flown aboard aircraft around the world and compared on return to identical clocks left behind. They disagree, and by exactly the predicted margin. The satellites of the global positioning system carry atomic clocks that tick at a measurably different rate from clocks on the ground below, in part because of their orbital motion. Were that difference not corrected continuously, navigation errors would accumulate at several kilometers per day, and the system would collapse into uselessness within a single morning. Each time a phone fixes its position, it depends on engineers having accepted that time runs differently for objects in different states of motion. What has quietly happened here is the loss of Newton's universal clock. There is no single rate at which time advances, because the rate depends on motion and different things move differently. Every observer carries a clock that is entirely valid, and not one of those clocks can claim to be the true one against which the others are wrong. Time has become local, particular, bound to the individual path each object traces through the world. And once time forfeits its universality, once no master clock remains to coordinate all the rest, a further assumption begins to look unstable. If clocks in relative motion cannot agree on how much time has passed, it is worth asking whether observers can still agree on something that seems far more basic, whether two distant events happen together at all. The answer, worked out from the same two principles, is that they cannot. And this is where relativity stops merely bending clocks and begins dismantling the idea of a shared present. The disagreement even has a name. Physicists call it the relativity of simultaneity. And of all the theory's consequences, it may be the one that does the most damage to ordinary intuition, because it strikes at something we never think to question. We assume that the word now means the same thing for everyone. Whatever is happening at this instant here is matched by things happening at this same instant everywhere else, across the room, across the country, across the reach of space. Two events either happen together or they do not, and that fact should not depend on who is looking. Relativity shows that it does depend on who is looking, and specifically on how they are moving. To see why, it helps to understand how the theory defines simultaneity in the first place, because the trouble hides inside the definition. Suppose you want to decide whether two events at different places happened at the same time. You cannot simply be present at both, because they are separated in space. You need a procedure, and the natural one uses light, since light is the fastest signal reality permits, and its speed is the fixed anchor the whole theory rests on. Imagine standing exactly halfway between 2 points. If a flash reaches you from each point at the same instant, and you know you are equidistant from both, and light travels at the same speed in every direction, then you can reasonably conclude the two flashes were emitted together. This is not a loose intuition. It is an operational rule for establishing what at the same time actually means, and it looks completely sound. The difficulty appears only when a second observer, moving relative to the first, applies the very same rule to the very same events. Einstein illustrated this with a scenario that has become one of the most useful thought experiments in physics, and it needs no equations to follow. Picture a very long train moving down a straight track at high, steady speed. Two bolts of lightning strike the train, one at the front, one at the rear, and each leaves a scorch mark both on the train and on the track below, so there's a permanent record of exactly where each strike landed. Now, place two observers. One stands on the embankment beside the track, positioned precisely at the midpoint between the two scorch marks on the ground. The other rides inside the train, seated exactly at its middle, halfway between the marks burned into the carriages. The question is simple. Did the two lightning strikes happen at the same time? Begin with the observer on the ground. The light from both strikes travels toward this observer at the fixed speed of light. The observer sits at the midpoint, so the two flashes have equal distances to cover. If they arrive together, the ground observer concludes, correctly by the agreed procedure, that the strikes were simultaneous. Suppose that is exactly what happens. For the person on the embankment, front and rear, lightning struck at the same moment. There is nothing controversial in this. It is simultaneity established by the book. Now consider the passenger at the center of the train and follow carefully what the situation looks like for that person, because everything turns on it. During the interval, it takes the light to travel from the strike points to the middle of the train. The train itself is moving forward. The passenger, seated at the center, is carried forward along with it. This means the passenger is moving toward the point where the front bolt struck, and away from the point where the rear bolt struck. The light coming from the front therefore has a shorter distance to cross to reach the passenger, because the passenger is closing the gap. The light from the rear has a longer distance to cover, because the passenger is pulling away from it. And here, the constancy of light becomes decisive. Both flashes travel at the same speed for the passenger, exactly as for everyone. Neither is sped up or slowed by the motion of the train. So the flash with the shorter distance to travel arrives first. The passenger sees the front lightning before the rear lightning. The passenger, applying precisely the same reasoning the ground observer used, reaches a different verdict. Sitting at the exact middle of the train, equidistant from the two scorch marks on the carriage, and knowing light travels at a fixed speed in both directions, the passenger sees the front flash arrive earlier and concludes that the front strike happened first, followed a moment later by the rear. For the passenger, the two events were not simultaneous at all. They were separated in time, front before rear. Nothing here is a mistake, and this is the point that has to be absorbed rather than skimmed. Neither observer has miscounted or measured badly. Neither has been fooled by an illusion of perspective, the way a distant object merely looks small while remaining its true size. Both have followed the correct identical procedure. Both are equally entitled to trust their result. The ground observer is right that the strikes were simultaneous. The passenger is right that they were not. There is no further fact, no view from outside, that settles which of them describes what really happened, because in relativity, there is no privileged standpoint from which the true timing could be read off. Simultaneity is not a fixed feature of the events themselves. It is relative to the observer's motion. Whether two separated events happen at the same time genuinely has no single answer. It is worth pausing to feel the weight of that, because it is easy to nod along without registering how strange it is. In the Newtonian world, whether two events were simultaneous was a plain matter of fact, as definite as whether they occurred at all. Two things happened together or they did not, and every conceivable observer would agree, because they all read the same universal clock. That clock is now gone, and with it goes the shared present. The question of what is happening right now at some distant place no longer has one correct answer. It has as many answers as there are states of motion, and none of them outranks the rest. Consider how far this reaches. At this instant, as you sit still, you have some notion of what is happening now on the far side of the world, or on Mars, or in a galaxy millions of light years away. Relativity says that notion is tied to your particular motion. Someone walking past you at a stroll, moving at a few kilometers per hour, has a slightly different now for those distant places, a plane of simultaneity tilted a little from yours. For nearby events, the tilt makes almost no measurable difference, because the geometry that produces it depends on both relative speed and distance. and over short distances the effect is far too small to notice. But the tilt is real, and over vast distances it grows. A gentle difference in motion here, spread across the enormous gulf between galaxies, can shift the corresponding now by huge intervals. Two people passing on a sidewalk, doing nothing more dramatic than walking in opposite directions, can have present moments for a distant galaxy that differ by many years. One person's now for that galaxy might include an event that, for the other person, still lies in the future, unhappened. This is not a matter of communication delay or of when light from distant events reaches us. That is a separate and simpler point, familiar enough that we see distant things as they were when the light left them. The relativity of simultaneity is deeper. It concerns not when we observe an event, but when the event happens, in the observer's own reckoning after every delay has been accounted for and subtracted out. Even after correcting perfectly for the travel time of light, two observers in relative motion still disagree about which distant events are happening now. The disagreement is not about perception, it is about the structure of time itself. Once this is accepted, the ground beneath the flowing present starts to give way, and it is worth being precise about why. If there is no universal now, then the neat division of reality into a settled past, a fleeting present, and an open future cannot be a feature of the universe as a whole. That division depends entirely on there being a shared present moment to draw the line at, a single now that separates what has happened from what has not. But the present is different for every observer, tilting with their motion, so the line falls in a different place for each of them. What one observer counts as the settled, finished past, another observer, moving differently, may count as the present or even as the future not yet arrived, and each is equally correct. Think through what that forces us to conclude. If your now can include, as a definite present tense reality, an event that lies in my future, then that event must be every bit as real as any event in my present. It cannot be waiting in some misty realm of the not yet existent, because for you it is simply happening, part of the concrete world. And whatever is real for you, in a universe with no privileged observer, must be real. Full stop. There is no way to grant your present reality while denying it to the events it contains. The future event you count as present cannot be less real than the present events I count as present. Reality cannot be sliced up differently for different observers and still be one shared reality. So the events of the future, at least those that appear in some valid observer's present, must already exist, as fully and definitely as the events we call now. The lightning on the train seems a small thing, two flashes and a disagreement about their timing. But followed to its end, the disagreement pries apart the whole architecture of past, present, and future. It suggests that these are not real divisions carved into the universe, but labels each observer applies from their own moving vantage point, with no agreement possible and none required. The question that remains is, what kind of universe could hold all these tilted, conflicting nows at once and remain consistent? If no single slice through time is the true present, then perhaps the truth is not any slice at all, but the entire structure taken together, every event laid out and coexisting. To describe such a universe precisely, physics needed more than a set of paradoxes about trains. It needed a new geometry, one in which time was not a river running through space, but another dimension woven into it. That geometry arrived in 1908, and it came not from Einstein, but from one of his former teachers, a mathematician named Hermann Minkowski. Minkowski had taught Einstein at the Zurich Polytechnic and reportedly remembered him as a student not especially devoted to mathematics. Yet, when he examined what his one-time pupil had produced, he recognized something Einstein himself had not fully drawn out. The relativity of simultaneity, the elastic clocks, the contracting lengths, all of these scattered consequences pointed toward a single underlying picture, and that picture was geometric. The disagreements between observers were not a sign of confusion in the theory. They were exactly what one would expect if space and time were not two separate things, but two aspects of one unified entity. Minkowski gave that entity its name, space-time, and in a lecture that year, he delivered a line that has echoed through physics ever since, declaring that space by itself and time by itself were destined to fade into shadows, and only a union of the two would preserve an independent reality. To understand what he meant, it helps to start with the ordinary geometry of space alone, because the leap to spacetime is best made from familiar ground. Think of a flat map. Any point on it can be pinned down with two numbers, a distance east and a distance north, say. Those two numbers are coordinates, and they locate a position on the two-dimensional surface. Add a third number for height, and you can locate any point in the three-dimensional space of the room around you. This much is intuitive. We live in three spatial dimensions and move through them freely, forward and back, left and right, up and down. A location in space is three numbers. Minkowski's move was to treat an event, something that happens at a particular place and a particular time, as a point specified by four numbers. Three of them give its position in space as before. The fourth gives its time. A flash of lightning striking the front of that train is not just a location. It is a location together with a moment, and to pin it down completely requires all four numbers. Minkowski proposed taking this literally, treating time as a genuine fourth dimension alongside the three of space, and treating the universe as a four-dimensional structure in which every event occupies a fixed point. In this framework, a point is not merely where something is, it is where and when something happens, and physicists call such a point an event in the technical sense, a single specified happening at one place and one time. This four-dimensional arena is now known as Minkowski spacetime, and to work within it, physicists picture a kind of diagram, though the full version cannot truly be drawn, since paper offers only two dimensions and a full spacetime needs four. The standard compromise is to flatten space down to a single line running horizontally, sacrificing two of its three dimensions, and to let time run vertically up the page. On such a diagram, a single point still represents an event, a particular place at a particular moment. But something more interesting appears when you consider an object that persists through time, which is to say any object at all. A rock sitting on the ground is not a single event. It exists at this place at one moment, at the same place a moment later, and so on continuously. On the space-time diagram, the rock is not a point, it is a line, tracing upward through time, marking where the rock is at every successive instant. This line is called the object's world line, and it is one of the most important ideas in the whole framework. Every object that endures has a world line, a continuous track through space-time recording its entire history. A person's world line begins at birth and threads through every place they ever occupy, every room, every journey, every moment of stillness, until it ends at death. A planet's world line is a long helix, spiraling as it orbits its star, while the star itself carries it through the galaxy. A photon of light traces its own world line across the cosmos. Nothing that exists in time is exempt. To exist at all in this picture is to be a world line, an extended thread laid out through the four-dimensional structure, rather than a small present-tense object that moves. And this reframing is where the erosion of flowing time accelerates, because a world line does not move, it simply is. The rock does not travel up its world line the way a train travels down a track. The world line is the rock's whole existence, already complete, laid out along the time dimension in its entirety. This is the point at which the geometry starts to reshape intuition rather than merely record it. When we picture an object moving, we imagine it at one position now, and we think of its future positions as not yet real. As possibilities, the object will arrive at once, time carries it there. The space-time picture refuses that division. In it, the object's future positions are already present in the structure, further along the world line, no less real than the position we happen to call now. Nothing needs to arrive anywhere. The entire world line exists at once, a fixed feature of the four-dimensional whole, in the same way that the entire length of a road exists at once, even though a traveler encounters its miles one after another. The traveler's sense of arriving at each new mile does not mean the far miles were unreal until reached. They were there the whole time, waiting only to be encountered. Minkowski's geometry invites us to see time the same way. The future stretches of a world line are as real and as present in the structure as the stretch we currently inhabit. There is a precise reason the geometry compels this reading, and it returns us to simultaneity. Recall that observers in relative motion disagree about which events happen at the same time. In the language of space-time, this disagreement has an exact geometric meaning. To carve the four-dimensional structure into a sequence of present moments, one must slice it, taking all the events that count as simultaneous and grouping them into a single slice, a three-dimensional snapshot of everything happening now. Stack these slices in order, and you recover the familiar sense of time as a succession of present moments, one after another. But here is what Minkowski's geometry makes vivid. The relativity of simultaneity means different observers slice the structure at different angles. An observer at rest slices it one way. An observer in motion slices it along a tilted plane, gathering a different set of events into their now. The four-dimensional block is the same for both. Only the slicing differs. Think of it through a physical image that captures the mathematics faithfully. Picture a loaf of bread, whole and uncut, representing the entire four-dimensional space-time, all of history, and all of the future together in one solid object. To experience time as flowing is to cut the loaf into slices and encounter them one at a time, each slice a single present moment, the whole sequence giving the impression of time passing as you move from one slice to the next. Now the crucial part. Different observers cut the loaf at different angles. Someone at rest cuts straight down, producing one set of slices. Someone in motion cuts on a slant, producing a different set, each of their slices containing a different mixture of what the first observer would call past, present, and future. Both are cutting the same loaf. The loaf does not change. What changes is only the angle of the cut, the orientation of each observer's present through the fixed and shared structure. This image clarifies why the block must be regarded as fully real in all its extent. If the loaf did not already exist as a whole, in all its length, then the slanted cuts would have nothing to slice. The moving observer's present includes events that the resting observer places in the future. For that present to be a coherent, real snapshot, those future events must already be there in the loaf, fully baked, waiting to be cut. You cannot slice a loaf that is not finished rising. The very fact that different observers can validly disagree about which events are present requires that all the events across all of time exist together in the structure to be sliced in these various ways. The relativity of simultaneity, expressed geometrically, is not merely consistent with a block universe. It seems to demand one. Minkowski's contribution, then, was not simply a convenient way to draw relativity. It was a claim about what relativity means. Einstein had shown that clocks and rulers behave strangely for observers in relative motion. Minkowski showed that this strangeness dissolves the moment one stops thinking of space and time as separate and starts thinking of them as a single four-dimensional geometry. In that geometry, the strange effects are not strange at all. They are the natural consequences of different observers taking different paths and cutting different slices through one unchanging structure. Einstein, who had at first regarded his old teacher's reformulation as an unnecessary mathematical embellishment, came to see it as essential. When he later built his theory of gravity, general relativity, he built it entirely on the foundation of four-dimensional spacetime that Minkowski had laid. The geometry was not decoration, it was the thing itself. And so the picture assembles into something coherent, if deeply at odds with experience. There is no universal clock, because clocks run at rates that depend on motion. There is no shared present, because observers slice their nows at different angles. And underlying both of these facts, there is a single four-dimensional structure, space-time, in which every event holds a fixed position and every object is a complete world line laid out from beginning to end. What we call the passage of time appears in this framework to be the experience of moving along a world line, encountering its events in sequence, though the events themselves are all equally present in the structure, none of them coming into being and none passing away. Yet, a thought experiment about lightning and a loaf of bread can only carry conviction so far. If the tilting of the present is real and not a mere abstraction of the mathematics, it ought to produce concrete consequences, situations where the disagreement about now becomes not a matter of angle on a diagram, but a difference of years, reaching across real distances in the actual sky. Such a case exists, and it involves nothing more exotic than a person taking a few steps down a street. The case is known as the Rietvdijk-Putnam argument, or more commonly the Andromeda paradox, and it was framed independently in the 1960s and 70s by the philosophers C.W. Rietvdijk and Hilary Putnam as a way of showing that relativity's consequences for the present are not confined to trains and thought experiments. They reach into the everyday, into the ordinary act of walking, and they do so with a specific and startling number attached. The argument takes the tilting of simultaneity established in the previous reasoning and applies it to a real astronomical distance, the gap between our galaxy and the Andromeda galaxy, our nearest large neighbor, lying roughly 2.5 million light-years away. What emerges is a demonstration that two people standing in the same spot, differing only in how they move, can have present moments for that distant galaxy separated by days and under slightly different conditions by far longer. Set the scene carefully, because the power of the argument lies entirely in its details. Two people stand side by side on a sidewalk at the same place on the same evening, looking up at the same sky. One of them is standing still, the other is walking at a completely ordinary pace, the speed of a casual stroll, a few kilometers per hour, and let us say they are walking in the direction of Andromeda, toward that faint smudge of light in the constellation of the same name. By every measure that matters in daily life, these two people share a moment. They are neighbors in space, breathing the same air, seeing the same stars. If you asked either of them what is happening right now in the Andromeda galaxy, you would expect them to give, if not a knowable answer, at least the same answer in principle. They occupy the same here and surely the same now. Relativity says otherwise, and the reason traces directly back to the tilted planes of simultaneity. Recall that an observer's present, extended out to distant places, depends on their state of motion, and that the tilt of this plane grows with distance. Over the span of a room, the effect is immeasurably small. Over the 2.5 million light-years to Andromeda, it becomes substantial. The person standing still has one plane of simultaneity, one particular slice through the four-dimensional structure that defines what counts as now across the cosmos. The person walking toward Andromeda has a plane tilted very slightly relative to the first, because they are in motion. That slight tilt near at hand would shift the corresponding now by an amount too small to detect. But projected across millions of light-years, the same small tilt sweeps through an enormous span of time at the far end. The arithmetic, worked through with the geometry of relativity, yields a figure that is easy to state and hard to absorb. For the 2.5 million light-year distance to Andromeda, a walking speed of a few kilometers per hour tilts the plane of simultaneity by enough to shift the present moment there by several days. The precise number depends on the exact speed and distance chosen, but the order of magnitude is robust. The person standing still has a now for Andromeda that corresponds to one particular day in the history of that galaxy. The person walking toward it at strolling pace has a now that corresponds to a different day, several days further along in Andromeda's history. And crucially, if the walker turns around and strolls in the opposite direction, away from Andromeda, their plane tilts the other way, and their present for the galaxy shifts several days into what the first slicing would call the past. Simply by choosing which way to walk, a person selects a different present moment for events unfolding millions of light-years away. Consider what this means with a concrete example, because the abstract statement can slide past without landing. Suppose that in the Andromeda galaxy some decisive event is taking place, and to make it vivid, imagine it as a fleet of ships departing on a long voyage, or the ignition of some great process, anything that has a definite before and after separated by a few days. For the person standing still on the sidewalk, that departure has not yet happened. It lies in their future. The fleet has not left. For the person walking toward Andromeda, at the very same instant on the very same sidewalk, the departure has already occurred. The fleet is gone. It is in their past. Both are looking at the same galaxy at the same time by any ordinary reckoning, standing centimeters apart, and yet one of them has a present in which the event is still to come, and the other, a present in which it is already history. Neither is wrong. There is no third correct answer that overrules them. The event is future for one and past for the other, and the only difference between these two people is the direction and fact of a leisurely walk. The force of the argument now becomes clear, and it is worth drawing out step by step rather than leaving it implicit. If the walker's present genuinely includes the fleet's departure as a real, already accomplished event, then that departure must exist. It cannot be a mere possibility, a thing that might or might not come to pass, because for the walker, it has definitely come to pass. It is settled, part of the fixed furniture of their present reality. But the stationary observer, standing right there, places that same departure in the future as something not yet real, not yet decided. Both observers are equally valid. Relativity grants no privilege to either. And here is the vice. If the event is real for the walker, and the walker's viewpoint is as legitimate as the stationary observer's, then the event must be real. Period. Reality cannot flicker in and out depending on who is walking past. An event either exists or it does not, and if any valid observer's present contains it as an accomplished fact, then it exists. But that event was, for the stationary observer, in the future. So a future event, something that from the stationary standpoint has not yet happened, must nonetheless already exist, because it is present and real for someone else standing in the same place. And there's nothing special about this particular event or this particular pair of observers. The reasoning applies to any event anywhere, and to observers moving in any direction at any speed. For any event you might name, however far in the future it seems from where you stand, there exists some possible observer, moving in some ordinary way, for whom that event is present and therefore real. Since all these observers are equally valid, the events they variously call present must all be equally real. The conclusion is that every event, past, present, and future without distinction, exists. The future is not a region of unformed possibility waiting to be actualized. It is already there, as concrete and settled as the past, differing only in that we have not yet encountered it along our own world line. It is worth pausing to address the natural resistance this provokes, because the mind reaches immediately for an escape. Surely, one wants to say, this is just about the delay of light, about the fact that we see Andromeda as it was 2.5 million years ago, and so all this talk of its present is meaningless anyway. But that objection misses the structure of the argument entirely. The disagreement between the two observers is not about what they see. Both of them, if they looked, would see exactly the same ancient light from Andromeda, the same image from millions of years past, because they are standing in the same place, and the light reaching that place is the same light. The disagreement is about which distant event is simultaneous with their standing there, after all the travel time of light has been calculated and subtracted out. It concerns the true timing of the event in each observer's own accounting, not the visual appearance delayed by distance. The two nows differ, even though the two views are identical. That is precisely what makes the argument bite. One might try another escape, insisting that the walker's tilted present is somehow less real than the stationary observer's, that there must be a true state of rest, and a true now against which the walker's slanted slice is merely a distortion. But this is exactly the possibility relativity forecloses. There is no state of true rest. The stationary observer is only stationary relative to the sidewalk, which is riding a spinning planet, orbiting a star that is itself hurtling through a galaxy, drifting through the expanding cosmos. Motion is entirely relative. There is no privileged observer whose slicing is the correct one, and against whom all others are askew. Every uniformly moving observer has an equal claim to define the present, and their disagreements cannot be resolved by appeal to any master frame, because no master frame exists. This was the lesson of the Michelson-Morley result carried to its end, the lesson that there is no ether, no fixed stage, no absolute rest. Without that stage, there is no way to crown one now as real and dismiss the others. So the Andromeda paradox is not really a paradox in the sense of a contradiction to be resolved. It is a demonstration, a way of forcing into the open a conclusion that the geometry of space-time contained all along. The relativity of simultaneity, harmless seeming when confined to lightning and trains, turns out to imply, when applied across cosmic distances, that the future exists as surely as the past, and that the division of time into settled history and open possibility cannot be a real feature of the universe. What we have been circling through trains and loaves and walks now stands stated plainly, though not yet named or given its full philosophical weight. The scattered consequences of relativity have converged on a single startling proposition about the nature of existence itself, and it is time to state that proposition directly, to give it its proper name, and to examine exactly what it does and does not claim. The proposition is called eternalism, and its central claim can be stated in a single sentence. All events in time, past, present, and future, are equally real. The dinosaurs are not gone. Your birth is not a vanished event that once existed and now does not. The moment of your death, whenever and however it comes, already exists. Every instant of history and every instant yet to unfold occupies its fixed place in the four-dimensional structure of space-time, and no instant is privileged with a special status called existing now, while the others languish in non-existence. This is the view that relativity, followed to its conclusions, appears to support, and it stands in stark opposition to the way nearly every human being instinctively understands time. To see clearly what eternalism asserts, it is useful to set it against its principal rival, the view most people hold without ever having named it. That view is called presentism, and it is the natural philosophy of time embedded in ordinary language and thought. Presentism holds that only the present moment is real. The past was real but is no longer, having slipped out of existence the instant it passed. The future is not yet real, being a realm of possibility that does not exist until it arrives and becomes present. On this view, reality is a single fleeting instant, the now, constantly renewing itself, with the past dissolving behind it and the future condensing ahead of it. Existence is confined to the razor-thin edge of the present, and everything else, all of history and all of what is to come, has either lost reality or not yet gained it. This is how time feels. It is almost certainly how you have always thought about it, whether or not you ever put it into words. Eternalism denies all of this. It says the past has not lost reality and the future has not failed to gain it. The distinction between past, present, and future is not a distinction between what has ceased to exist, what exists, and what does not yet exist. It is more like the distinction between here and there. When you say a place is there rather than here, you do not mean it fails to exist. A city on the far side of the planet exists just as fully as the room you occupy, even though you are not in it. It is simply elsewhere in space. Eternalism proposes that past and future moments are, in the same way, simply elsewhere in time. They exist as robustly as the present moment. You are merely not located at them. The word now, on this view, functions exactly like the word here. It picks out the speaker's own position, in time rather than in space, and it says nothing about which moments are real, just as here says nothing about which places are real. Every moment is now to itself. In the same way, every place is here to someone standing in it. This is why the block universe is the natural picture that accompanies eternalism. If all moments are equally real, then reality is not a moving present sweeping through time, but a static, complete, four-dimensional whole containing every event in its proper place. The block does not change because change, in the ordinary sense, would require some moments to be real, and others not, with the boundary between them shifting. But in the block, all moments are real together. Nothing comes into being and nothing passes away, because being is not something a moment acquires and then loses. The universe simply is, laid out in four dimensions, timelessly. It is worth being careful with that word timelessly, because it does not mean the block contains no time. The block contains time in abundance. Time is one of its four dimensions, fully present, along which events are ordered as earlier and later. What the block lacks is not time, but the passage of time, the flowing, the coming into being and slipping away. Time exists in the block as a dimension. It simply does not flow. An analogy sharpens the distinction, provided it is handled with care. Consider a film reel, the old kind, a long strip of celluloid on which thousands of individual frames are printed in sequence. Every frame exists on the strip at once. The frame showing the opening scene and the frame showing the final scene are both physically present on the reel, side by side in the canister, equally real, neither more nor less there than the other. When the film is played, the projector illuminates one frame at a time in rapid succession, and this creates the experience of motion, of a story unfolding, of one moment giving way to the next. But that unfolding is an artifact of the projection, of the frames being lit one after another. The frames themselves are all there together, static, complete. The block universe, on this analogy, is the whole reel. Our experience of time passing is like the illuminated frame moving along it. The difference, and it is a profound one, is that in the block there is no projector and no external light moving from frame to frame. There is nothing outside the structure doing the illuminating. But as a picture of how every moment can be equally real while we experience only one at a time, the reel captures the essential idea. All the frames exist. We simply encounter them in order. Now, it must be said plainly that eternalism is not a proven fact, and honesty about its status matters. It is an interpretation, a philosophical position about what relativity implies, and it is contested. The physics of relativity is not in doubt. The time dilation, the length contraction, the relativity of simultaneity, all of this is experimentally confirmed beyond serious question and used daily in working technology. What remains open is what this physics tells us about the ultimate nature of time. Eternalism is one reading, and to many physicists and philosophers it is the most natural one, because it takes the four-dimensional geometry of space-time at face value and refuses to smuggle back in a flowing present that the mathematics never contained. But it is a reading, and there are those who resist it, who believe the passage of time is too fundamental to our experience to be dismissed as illusion, and who look for ways to reconcile the physics with a genuine, flowing now. Their efforts will matter later. For now, the point is that eternalism is a serious and widely held position, not a settled result, and that its strength comes from how cleanly it fits the structure of relativity. The case for it, assembled from everything established so far, runs as a chain of steps, and laying them out in order shows how much weight the conclusion carries. First, relativity is correct, confirmed by a century of precise experiment. Second, relativity entails the relativity of simultaneity, the fact that observers in relative motion disagree about which distant events are present. Third, as the Andromeda argument showed, this means that for any event you might name, there exists some valid observer for whom that event is present and therefore real. Fourth, since all observers are equally valid, with no privileged frame to crown one as correct, the events that these various observers count as present must all be equally real. Fifth, therefore, every event, whenever it occurs in the ordinary reckoning of past, present, and future, is real. That is eternalism. Each step follows from the one before, and the only ways to reject the conclusion are to reject the physics, which the experiments forbid, or to find a flaw in the chain of reasoning, which many have tried to do and none has done decisively. It is worth dwelling on how radically this revises the ordinary picture, because the temptation is always to nod at the argument and then quietly continue thinking about time in the old way. Under eternalism, nothing that has ever happened is truly lost. Every moment of every life that has been lived remains fixed in its place in the structure, as real as this moment. A conversation held years ago has not vanished. It exists at its own location in time, being had permanently. This is not a claim that we can return to it or perceive it again from where we stand. We cannot travel back along our world line any more than we can be in two places at once, but its reality does not depend on our access to it, just as the far side of the planet does not stop existing because we cannot see it from here. And by the same logic, the events of the future, including the ones we agonize over and strive toward and dread, are already laid down. The structure is complete, what we call deciding, striving, waiting to see how things turn out. All of it unfolds along world lines whose full extent already exists. This is where eternalism becomes not merely a curiosity of physics, but a claim that presses directly on human experience, and where the most natural objection to it grows almost impossible to suppress. If every moment already exists, if the future is as fixed and real as the past, if nothing genuinely comes into being or passes away, then why does it so overwhelmingly seem otherwise? Why do we feel time moving? The sensation of the present sliding forward, of moments arriving and departing, of a now that is vividly real in a way that memories and anticipations are not, is not a subtle or occasional feeling. It is the constant texture of conscious life, the most immediate fact of existence. A theory that declares this feeling to be in some sense a misreading of reality owes an account of why the misreading is so total and so universal. If the block is real and time does not flow, then the flowing we experience must come from somewhere, and explaining its source is the next demand the theory must meet. The problem can be stated with uncomfortable precision. Eternalism claims the block universe is static, that no moment is objectively present and no time truly passes. Yet the passage of time is the single most insistent feature of everything we experience. Right now, as these words are read, there's a vivid sense of a present moment, sharp and alive, quite unlike the dim recollection of an hour ago or the vague anticipation of an hour hence. That present seems to be moving, sliding forward, so that the moment now current will shortly be past, and a moment now future will shortly be present. If the physics says this movement is not a feature of the universe, then the burden falls squarely on the physics to explain why we are so completely and continuously convinced that it is. A theory cannot simply declare the most basic fact of experience to be an error and walk away. It has to say where the error comes from. The first thing to notice is that the sense of a flowing present is not delivered to us by any physical measurement. This is easy to overlook, so it is worth stating carefully. No instrument detects the present moment. A clock does not measure the flow of time. A clock measures durations, intervals between events, how much time separates one tick from another. It counts. It does not point to a special moment and announce, "This one is now." If you photograph a clock, the photograph shows a particular reading, but nothing in the photograph marks that reading as the present as opposed to a past reading captured earlier. Every clock reading is simply a position along the time dimension, and no reading is physically distinguished as the live one. The nowness we feel so strongly attaches to no measurable quantity. It appears nowhere in the equations of physics, which contain time as a coordinate but contain no term for which value of that coordinate is present. The flow of time, whatever it is not found in the physical description of the world. It is found only in experience. That observation reframes the whole problem. The passage of time may not be a feature of the universe that our minds detect, but a feature of our minds that we project onto the universe. And once the question is posed that way, physics and neuroscience can begin to offer an account, not of why time flows, but of why a certain kind of information processing system, built as we are, would inevitably feel as though it does. The account is not complete, and parts of it remain genuinely open, but its outline is coherent, and it draws on facts that are not in dispute. Begin with memory, because memory is the hinge on which the sense of passage turns. We have records of the past. Our brains store traces of earlier events, and at any given moment we possess memories of what came before. We have no corresponding records of the future. There are no memories of tomorrow. This asymmetry is total, and it is the raw material from which the feeling of temporal flow is built. At any moment along your world line, your brain is in a particular state, and that state includes memories of earlier moments, but nothing from later ones. Consider what this means for how any moment must feel from the inside. Standing at any point on your world line, you find yourself equipped with a stock of memories of what you take to be the past, and equipped with nothing at all about the future. This gives every moment a built-in orientation, a direction, a sense of having come from somewhere and facing toward somewhere unknown. The past feels settled because you have records of it. The future feels open because you have none. The asymmetry of the feeling mirrors exactly the asymmetry of the information available at each point. Now, push the analysis further, because memory alone gives orientation but not yet motion, and it is the sense of motion, of the present actually moving, that most needs explaining. Consider not a single moment but the relationship between successive moments along the world line. Take a moment we can label the later one. At that moment, the brain contains memories of the earlier moments, and among those memories is a memory of having been at the earlier moment, while at that time anticipating the later one. In other words, at each point along the world line, the brain contains a record of the previous points, and those previous points themselves contained records of their previous points, and so on. The structure of memory is nested and cumulative. Each state of the brain, at each moment, carries within it an encoded summary of the states that came before. When you are at any given instant, you have access not just to that instant, but to a compressed trace of the whole run of instants leading up to it. This nesting is what generates the impression of flow. At each moment, you are aware of the current experience and, simultaneously, of remembering the previous ones, and this combination, current experience, layered over the memory of prior experience, feels exactly like having moved from those prior experiences to this one. The feeling of the present sliding forward is the feeling of occupying a state that contains, as memory, the states just behind it. There is no need for anything actually to move for this feeling to arise. At every point along the static world line, the brain state at that point contains the ingredients that produce the sensation of having just arrived from the previous point. The sensation of flow is present at every moment, generated locally by the structure of memory at that moment, without anything flowing. Each frame, to return to the earlier image of the film reel, contains within itself the record of the previous frames, and so each frame, considered on its own, carries the feeling of having come from them. Play the frames in no order at all, or in all orders at once as the block does, and each one still contains its own built-in sense of motion, because that sense is printed into the frame itself. An analogy makes the structure vivid. Imagine a very long series of photographs of a person taken one after another as they walk down a road. In each photograph, the person holds a notebook, and in the notebook, they have written a brief description of every photograph taken before this one. The first photograph's notebook is blank. The second describes the first. The 10th describes the first through 9th. The 1000th contains a long record of the entire journey so far. Now spread all 1,000 photographs on a table at once, static, complete, in no particular sequence. Pick up any single photograph and look at it. The person in it holds a notebook describing everything that led to that moment. From that photograph alone, in your hand, you would reconstruct a sense of a journey, of having traveled from the beginning up to this point, of momentum and direction and arrival. That sense is fully present in the single static image because the record of the past is printed in the notebook the figure holds. The photographs are not being played in sequence, they are all just lying there. Yet each one, examined alone, contains the felt sense of a journey completed up to it. Our moments are like those photographs. Each brain state, at each point on the world line, holds its notebook of memory, and each therefore carries within it the complete sensation of time having flowed up to that instant, whether or not any flowing occurs. There is more to the feeling than memory, and a fuller account brings in the way consciousness integrates the very recent past into what feels like a single present. The now we experience is not truly instantaneous. Perception takes time. The brain gathers signals from the senses, which arrive at slightly different moments and travel at different speeds, and it binds them together into a unified experience that seems to happen all at once. The present moment of experience is not a mathematical point, but a short interval, a smear of time a fraction of a second wide, which the brain assembles into the impression of a single instant. Within that constructed present, the brain is already relating what came a fraction of a second ago to what is arriving now, detecting change, tracking motion, registering that things are different from how they just were. This built-in comparison, running constantly, contributes directly to the feeling that time is passing, because the brain is continuously computing the difference between the just was and the is now, and that computation of difference feels like flow. The sense of motion in time may be, in part, the brain's ongoing detection of change within its own constructed present. None of this requires the block to be false. Every element of the explanation, memory, the nesting of records, the constructed present, the detection of change, is compatible with a static four-dimensional universe in which nothing flows. The explanation locates the flow not in the world but in the structure of the experiencing system. In the particular way, a memory-bearing, change-detecting brain must represent its own situation at each point along its world line. If this account is right, then the passage of time is real as an experience and unreal as a feature of the cosmos. It is something that happens in us, not something that happens to the universe. The flow is genuine the way a feeling is genuine, and illusory the way a feeling can misrepresent its cause. Yet even granting all of this, a hard residue of the problem remains, and intellectual honesty requires naming it. The account explains why each moment would carry a sense of orientation and a sense of having arrived from the past. What it explains less well is why there should be any experience at all of a single moving present rather than simply a collection of static moments, each with its own frozen contents. If all moments exist equally, why is there a felt now that seems to be here and not there? A particular moment lit up is the present while others are dark. This is bound up with the deepest unsolved problem in the study of the mind, the question of why physical processes are accompanied by any inner experience whatsoever. The block universe does not answer that question, and it does not have to. It needs only to show that its picture is consistent with the experience we have, that a static structure could contain beings who feel time flowing. That much it does. But the feeling of a present moment points toward a further mystery, and it connects to another asymmetry that the account has leaned on without yet examining. Memory runs one way. We remember the past and not the future. That one-way character of memory is a special case of something broader, a pervasive directionality that runs through the physical world itself, distinguishing earlier from later, even in a universe where time does not flow. To understand why the block has a grain to it, a direction, we have to turn from the mind to the physics of disorder. Here is a genuine puzzle at the heart of physics, and it sharpens the whole question of time's direction. Nearly every fundamental law that governs the universe works equally well running forward or backward. Write down the equations for how two particles collide, film the collision, then run the film in reverse, and the reversed film shows a collision that also obeys the laws perfectly. Nothing in the fundamental physics distinguishes the forward version from the backward one. The equations of motion, whether Newton's or Einstein's, or those of quantum mechanics in their basic form, are symmetric in time. They do not care which way time points. A process and its exact reverse are both entirely legal according to the deepest rules we have found. This property is called time reversal symmetry, and it presents a profound difficulty because the world of our experience is emphatically not symmetric in time. It has an obvious, insistent direction. The contrast could hardly be sharper. Drop a glass and it shatters on the floor, scattering fragments. You have never seen the reverse. Fragments do not gather themselves, rise from the floor, and assemble into a whole glass that leaps into your hand. Stir milk into coffee and it blends into a uniform brown. It never unstirs, the milk never gathering itself back into a separate white swirl. A hot cup of coffee cools to room temperature. A cold cup sitting in a warm room never spontaneously heats up while the room grows colder. Wood burns to ash and smoke, and the ash and smoke never recombine into wood. In every one of these cases, the forward process is utterly familiar, and the reverse is something we would regard as impossible, even miraculous. Yet the fundamental laws governing every atom in the glass, the coffee, the wood, permit the reverse just as freely as the forward. Each individual particle collision in the shattering of the glass would look perfectly lawful run backward. So where does the overwhelming directionality of the everyday world come from, if not from the fundamental laws? The answer, one of the most important insights in all of physics, lies in a quantity called entropy, and in the law that governs it, the second law of thermodynamics. Entropy is often described loosely as disorder, and that description is useful as a first approximation, but the precise meaning is more illuminating and worth taking care over. Entropy is a measure of the number of distinct microscopic arrangements of a system's parts that all look the same from the outside, that all correspond to the same overall large-scale state. This requires unpacking, because the distinction between the microscopic and the large scale is the whole key. Consider a room full of air. The large-scale state is what you could measure with ordinary instruments: the temperature, the pressure, the overall distribution of the gas. The microscopic state is the exact position and velocity of every single air molecule, of which there are an unimaginable number. Now, here is the crucial point. A great many different microscopic arrangements, a staggering number of different specific placements of all those molecules, correspond to the same large-scale state. If air is spread evenly through the room, there are countless ways to arrange the individual molecules that all yield the same uniform spread. But if all the air were bunched into one corner, leaving the rest of the room a vacuum, there would be vastly fewer arrangements consistent with that description, because you would be requiring every molecule to be in one small region rather than anywhere in the room. The evenly spread state corresponds to an enormous number of microscopic arrangements. The bunched-up state corresponds to a tiny number by comparison. Entropy counts these arrangements. High entropy means many microscopic arrangements produce the same overall appearance. Low entropy means few do. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time, moving from lower to higher, from fewer arrangements to more. And once entropy is understood as a count of arrangements, the reason for this law becomes almost obvious, which is part of its beauty. A system left to itself is constantly being jostled, its particles colliding and rearranging, effectively shuffling through possible microscopic arrangements. If there are vastly more arrangements corresponding to high-entropy states than to low-entropy ones, then a system randomly shuffling through arrangements is overwhelmingly likely to end up in a high-entropy state simply because there are so many more of them to land in. It is like shuffling a deck of cards. There is exactly one arrangement that counts as perfectly ordered, every suit together and in sequence. There are an astronomical number of arrangements that count as shuffled. Shuffle a deck and it becomes disordered, not because disorder is a force pulling on the cards, but because disordered arrangements are so overwhelmingly more numerous that a random shuffle almost certainly produces one. Order is rare. Disorder is common. Random change moves from the rare toward the common, from low entropy toward high, not by any law forcing it in that direction, but by sheer weight of numbers. This is why the glass shatters and never reassembles. A whole, intact glass is a low-entropy state, a highly ordered arrangement of matter, one of relatively few ways the atoms could be placed to constitute an unbroken glass. Shattered fragments scattered across the floor represent a high-entropy state, one of an enormous number of ways those atoms could be spread about as broken pieces. When the glass falls, the energy of impact shuffles its atoms, and they move overwhelmingly likely toward the more numerous disordered arrangement, shattering. For the fragments to reassemble, the atoms would have to shuffle, by chance, into one of the extremely rare arrangements constituting a whole glass, and simultaneously send exactly the right energy into lifting it off the floor. This is not forbidden by any fundamental law. It is simply so overwhelmingly improbable given how few arrangements correspond to the reassembled glass compared to the vast number corresponding to scattered fragments, that it never happens in the entire age of the universe. The arrow of time in everyday processes is statistical. It points from the improbable toward the probable, from the rare ordered states toward the common disordered ones, and it points that way because of counting, not because of any built-in direction in the underlying laws. Now, the connection to the block universe can be drawn, and it resolves something that might otherwise seem paradoxical. If the universe is a static four-dimensional structure in which time does not flow, how can there be a direction of time at all? The answer is that a direction is not the same as a flow. The block does not flow, but it has a grain, an asymmetry running along its time dimension, and that grain is the gradient of entropy. Along the time dimension of the block, entropy is arranged so that it is very low toward one end and increases steadily toward the other. This is not a process happening, it is a static feature of the structure, like the grain in a piece of wood, which runs in a definite direction through the wood without anything moving. The wood does not flow along its grain. The grain is simply there, an orientation built into the material. In the block universe, the entropy gradient is the grain of time. It gives the time dimension a distinguishable orientation, a difference between the two directions along it, even though nothing is flowing in either direction. The direction we call the past is the direction of lower entropy. The direction we call the future is the direction of higher entropy. Every asymmetry we associate with time's passage traces back to this gradient. We remember the past and not the future because memory formation is itself a physical process that depends on the entropy gradient. Recording a memory means creating an ordered trace, and creating and preserving such a trace requires an environment where entropy is increasing in a particular direction. Memory can only point toward the low entropy end, toward what we call the past, because that is the only direction from which stable records can be inherited. The reason our brains are stocked with records of earlier moments and not later ones is the same reason coffee cools and glasses shatter. It is all one asymmetry, the entropy gradient, showing up in different guises. The one-way character of memory that the previous account of temporal experience leaned on is not a separate fact. It is a consequence of this deeper grain in the structure of the block. This raises a question that reaches to the largest scales imaginable, and it is one physics takes with complete seriousness. If entropy increases toward the future because there are more high-entropy arrangements than low-entropy ones, then for entropy to have been increasing throughout all of history, the universe must have started in an extraordinarily low-entropy state. The past end of the block must be anchored in a condition of remarkably high order, an extremely improbable, extremely special configuration. Because only if the beginning was highly ordered could there be a long slope of increasing entropy stretching away from it. The direction of time in our entire universe, the whole grain of the block, depends on the fact that its early state, near the moment we call the origin, was one of astonishingly low entropy. Why the universe began in such a special, ordered, improbable condition is one of the genuinely open questions in cosmology. There is no settled answer. The low entropy beginning is, at present, simply a fact we observe and build upon, a boundary condition imposed at one end of the block for reasons not yet understood. What emerges from all this is a picture in which time can have a definite direction without flowing at all. The block is static, but it is not featureless. It is grained, oriented, asymmetric along its time axis, and every experience of temporal direction, every memory, every process that runs one way and not the other, expresses that single underlying asymmetry. The flow we feel is manufactured by our memory-bearing minds, as the earlier account described, but the direction that flow seems to have is not manufactured. It is real, printed into the structure of the universe as the slope of entropy from an ordered past toward a disordered future. This distinction between a direction that is real and a flow that is not is one of the most subtle and important that the block universe offers, but it presses immediately toward a further and more unsettling implication. If the future end of the block already exists, fully formed, as real as the past, and if every event along our world line is already laid down in the structure, then in what sense do we choose anything? If the moment of every decision and the outcome of every deliberation is already fixed in the block, waiting only to be encountered, the question of human freedom can no longer be postponed. If the block universe is real, then the future already exists, and everything you will ever do is already there, fixed in the structure, as settled and unchangeable as the events of 1,000 years ago. The choice you will make tomorrow is not waiting to be determined. It is already laid down along your world line, complete in every detail. The words you will speak, the decisions you will agonize over, the paths you will take, and the ones you will forego, all of them already occupy their places in the four-dimensional whole. This appears to leave no room for free will in any meaningful sense. If tomorrow's choice is already a fact, as real right now as yesterday's breakfast, then it is hard to see how it can be genuinely open. Hard to see how you could do otherwise than what the block already contains you doing. This is perhaps the most personally disquieting consequence of everything established so far, and it deserves to be examined carefully rather than either dismissed or accepted too quickly. The first thing to establish is that this challenge is real and not a confusion. Some responses to it try to dissolve the problem by pointing out that the future is not knowable, that no one can read the block in advance, and that our ignorance of what is coming preserves a kind of practical openness. But this misses the force of the difficulty. The problem is not about knowledge. It does not matter whether anyone can know the future. What matters is whether the future is fixed, and eternalism says it is, whether or not anyone can read it. A decision does not become free merely because its outcome is hidden. If the outcome already exists, settled in the structure, then it is settled regardless of who knows it. So the challenge cannot be waved away by appeal to our ignorance. It has to be met directly, and meeting it requires thinking carefully about what free will actually demands. It helps to recognize that this problem, in its essential form, is much older than relativity and does not depend on the block universe at all. Philosophers have debated for centuries whether free will is compatible with determinism, the idea that every event is fully caused by prior events according to fixed laws, so that given the state of the world at one moment, the next moment follows necessarily. Determinism, in this sense, was a live concern long before Einstein, arising naturally from the clockwork picture of the universe that Newton's physics suggested. If the present state of every particle determines the next, then the entire future unrolls inevitably from the past, and the same worry about freedom arises. The block universe presents essentially the same challenge in a different form. Whether the future is fixed because it is causally determined by the past, or fixed because it simply exists as part of the four-dimensional structure, the upshot for freedom seems the same. The future is settled. You cannot change it. So the vast body of thought that philosophers have devoted to the older problem applies almost directly to the newer one, and it offers more than one way to respond. The response that has come to dominate philosophical thinking is called compatibilism, and its central move is to look hard at what we actually mean and actually value when we speak of free will. The compatibilist argues that the freedom worth wanting was never the power to violate the laws of physics or to act without any cause. That kind of freedom, uncaused action springing from nowhere, would not even be desirable if we had it, because an action with no cause would be random, disconnected from your character, your reasons, your desires, arising from nothing. An action like that would not be more yours. It would be less yours, a spasm rather than a choice. What we actually mean by a free action, the compatibilist says, is something quite different and entirely compatible with the future being fixed. A free action is one that flows from your own desires, your own reasoning, your own character, without external compulsion. When you deliberate over a decision, weigh the considerations, and act on your conclusion, that action is free in the sense that matters, because it issues from you, from your values and your thinking, rather than being forced on you from outside. On this view, the fixity of the future does not threaten freedom, because the fixity operates through your choices rather than around them. Consider carefully how the future gets to be what it is in the block. Tomorrow's choice is fixed, yes, but what fixes it is not something external overriding your will. What fixes it is, in part, you, your deliberation, your reasons, your character, all of which are themselves part of the structure and part of the causal story. The block contains you deciding, and your deciding is a real process that genuinely produces the outcome. The choice is fixed as the choice you make, arrived at through your actual reasoning. It is not that the outcome is settled in advance and your deliberation is a pointless charade that makes no difference. Your deliberation is precisely the thing through which the settled outcome comes about. Remove your deliberation and the outcome would not be what it is. The block does not bypass your agency. It includes your agency as the very mechanism by which the future takes the shape it has. An analogy clarifies the point, though, like all analogies here, it must be handled with care. Imagine a decision you made in the past, a significant one, made after long and careful thought. That past decision is now completely fixed. It is over, settled, unchangeable, as much a part of the immovable past as anything can be. Yet you do not feel that its being fixed now means it was unfree when you made it. When you made it, you deliberated genuinely, weighed the options, chose according to your judgment. The fact that it is now settled and cannot be altered does not retroactively drain it of freedom. It was a free choice, and it is also a fixed fact. The compatibilist asks why the future should be any different. A future choice is fixed in the block the way a past choice is fixed in memory, but in both cases the fixity is the fixity of a choice actually made through genuine deliberation. If a past decision can be both settled and free, there is no reason a future one cannot be both as well. The only difference is which side of the present we stand on, and that difference, the block insists, is not a difference in the reality or the freedom of the choice. Still, there is a persistent intuition that resists all of this, and honesty requires giving it its due rather than declaring the matter closed. The intuition is that real freedom requires genuine alternatives, that for a choice to be free, it must be true that you could have done otherwise, and that if the future is fixed, then you could not have done otherwise, and so the choice is not free after all. This is the deepest form of the worry, and the debate over it is genuinely unresolved. The compatibilist has answers. They argue that could have done otherwise, properly understood, means something like would have done otherwise if you had wanted to or chosen to, which remains true even in a fixed universe, since the claim is about a dependence between your wanting and your acting, not about the future being open. The opponent of compatibilism, the one who insists freedom requires a truly open future, is not satisfied by this and holds that anything less than a genuinely branching set of possible futures is not freedom at all, but its imitation. There is no consensus. This is one of the oldest arguments in philosophy, and the block universe does not settle it. It simply presents it in a particularly stark and concrete form by making the fixity of the future not an abstract consequence of determinism, but a geometric feature of space-time. What the block universe does contribute is a certain clarity about what is and is not at stake. It makes vivid that the fixity of the future is not the same as fatalism, and this distinction matters enormously and is easily confused. Fatalism is the idea that the outcome will be the same no matter what you do, that your efforts are pointless because the end is fixed regardless of your choices. This is a misreading of the block, and it is worth stating clearly why. The block does not say the future is fixed independently of your actions. It says the future is fixed, and your actions are part of what fixes it. The outcome is not settled in a way that makes your striving irrelevant. Your striving is woven into the settled outcome as one of its causes. If you were to stop striving, the future would be different, because your striving is part of the structure that produces it. What the block forbids is not the efficacy of your actions, but the existence of alternatives to the actual course of events. Your actions matter completely. They simply have, as everything does, only one actual outcome, already present in the structure. To imagine that you could sit back and let the fixed future arrive without your participation is to misunderstand the picture entirely, because the fixed future includes, essentially, your participation in bringing it about. There's a certain relief available in this, though it sits alongside the unease rather than replacing it. The block universe does not turn us into passengers, carried helplessly along a predetermined track, while our sense of choosing looks on uselessly. It makes us participants whose deliberations and choices are real events that genuinely shape the structure of which they are part. The experience of weighing options and deciding is not a fiction laid over a process that would happen anyway. It is the process. What changes under the block is only the metaphysical status of the alternatives we did not choose. They were never going to happen, not because something prevented them, but because the one course that did happen is the one that is real. Whether this constitutes freedom in the fullest sense remains, as it has for centuries, a matter of genuine dispute. But it is at least clear that the block does not reduce us to spectators of our own lives. Yet all of this reasoning has proceeded on an assumption that deserves to be questioned, an assumption that has quietly underpinned every argument since the beginning. The entire case for the block universe and for the fixed future it entails has rested on relativity, and relativity describes a world that is, at its foundation, deterministic and smooth. But relativity is not the only pillar of modern physics. There is another theory, equally well confirmed, equally fundamental, that describes the world at its smallest scales, and it tells a very different story about the future. In quantum mechanics, the future does not appear to be fixed at all. It appears to be genuinely, irreducibly open, a matter of probability rather than certainty, with outcomes that seem not to exist until they occur. If that is right, then the tidy four-dimensional block, with every event already in its place, may face its most serious challenge not from philosophy or intuition, but from physics itself. Quantum mechanics presents the block universe with a problem that cannot be dismissed as mere intuition or philosophical preference, because it comes from within physics itself, from a theory every bit as well tested as relativity. At the scale of atoms and particles, the world does not behave in the smooth, determined way that relativity's four-dimensional structure seems to require. Instead, it behaves probabilistically. When a radioactive atom sits waiting to decay, there is no fact, as far as the theory can tell, about exactly when it will do so. There is only a probability, a likelihood of decay within a given span of time. Two identical atoms, prepared in exactly the same state, will decay at different moments, and nothing in their prior condition determines the difference. The outcome appears to be genuinely random, not merely unknown to us, but undetermined in the world. And if outcomes are genuinely undetermined until they happen, then the future cannot already exist, laid out and fixed in the way the block universe insists. There would be nothing there yet to lay out. The future would be open in the most literal sense, not yet written, not yet real. To see the depth of the difficulty, it helps to understand what quantum mechanics actually says about a system before it is measured, because the strangeness is more radical than mere randomness. A quantum system, such as a single particle, is described by something called a wave function, which does not specify a definite state, but rather a spread of possibilities, each with an associated probability. A particle, before it is measured, does not have a definite position. Its wave function assigns probabilities to a whole range of possible positions, and in a precise sense, the particle is best described as being in a combination of all of them at once, a condition called superposition. This is not a statement about our ignorance of where the particle really is. The evidence indicates that the particle genuinely does not have a single definite position until a measurement is made. The superposition is real, and it produces observable effects, patterns of interference that could only arise if the particle truly explored multiple possibilities simultaneously rather than secretly occupying just one. Then a measurement is made, and something dramatic happens. The spread of possibilities collapses to a single definite outcome. The particle, which had no definite position, suddenly has one. The wave function, which described a range of possibilities, is replaced by a single actuality. This event is called the collapse of the wave function, and it is here that genuine randomness enters, because which outcome the collapse produces is not determined by anything. The theory gives only the probabilities. It says this outcome will occur with such and such likelihood, that outcome with such and such other likelihood, but it does not and apparently cannot say which will actually happen on any given occasion. The specific result seems to spring into being at the moment of measurement, unfixed until that instant, produced by nothing that came before. This is the aspect of quantum mechanics that appears to slam directly against the block universe. If reality contains events that are genuinely undetermined until they occur, then those events cannot already exist in a fixed four-dimensional structure. The block seems to require a determinism that quantum mechanics denies. But the situation is far less settled than this presentation suggests, and the reason is one of the most important facts about quantum mechanics that non-specialists often miss. The collapse of the wave function, the introduction of genuine randomness, is not actually part of the core mathematics of the theory. The equation that governs how a quantum system evolves over time, called the Schrödinger equation, is entirely deterministic and smooth. Left to itself, a wave function evolves in a completely predictable way, spreading and changing according to fixed rules with no randomness whatsoever, and crucially, no collapse. The equation never produces a collapse. It never selects a single outcome. It just keeps evolving the full spread of possibilities, deterministically, forever. The collapse is something added on top of the equation, an extra rule stitched into the theory by its founders to account for the fact that when we actually measure something, we find a single definite result rather than a spread. This extra rule, describing when and how the smooth evolution gives way to a sudden random jump, is not derived from the mathematics. It is imposed by hand, and it has been a source of unease since the theory's earliest days. The question of what really happens during measurement and whether collapse is a real physical event or something else entirely is called the measurement problem, and it remains one of the great unresolved questions in physics. This matters enormously for the block universe, because whether quantum mechanics threatens the block depends entirely on how the measurement problem is resolved, and there are several competing resolutions, each painting a completely different picture. Consider the most striking of them, an interpretation that dispenses with collapse altogether. If the collapse is not part of the fundamental equation, one might ask what happens if we simply take the equation at its word and deny that collapse ever occurs. This is the proposal known as the many worlds interpretation, and it takes the deterministic Schrödinger equation as the complete and literal truth, with no collapse added. On this view, when a measurement is made, the wave function does not collapse to a single outcome. All the outcomes happen. The apparent randomness we observe is an illusion arising from our own position within the process. The reasoning runs as follows, and it is worth following carefully because it dissolves the quantum threat to the block in an unexpected way. When a particle in a superposition of possibilities interacts with a measuring device and ultimately with the physicist observing it, the smooth evolution of the equation does not pick one outcome. Instead, it entangles the device and the observer with the particle so that the whole combined system enters a superposition. There comes to be a version of the measuring device that recorded one outcome and a version that recorded another, and correspondingly, a version of the observer who saw the first result and a version who saw the second. The equation does not choose between these. It contains all of them. The universe, on this view, effectively splits, or rather branches, into multiple versions, one for each possible outcome, all equally real, all continuing to evolve. Each version of the observer finds themselves in a single branch, seeing a single definite result, and has no access to the others. The randomness you experience is simply the fact that you cannot predict which branch you will find yourself in, even though all branches occur. There is no genuine collapse, no genuine randomness in the fundamental sense, only a deterministic equation producing an ever-branching structure of coexisting realities. If the many worlds interpretation is correct, the block universe survives intact and in fact is enlarged. The future is not open and undetermined after all. Every possible outcome exists, laid out in the four-dimensional structure, or rather in a vastly larger structure containing all the branches together. Nothing is undetermined because everything happens. The apparent randomness that seemed to threaten the fixed future turns out, on this reading, to be perfectly compatible with a completely determined reality, one that simply contains far more than we ordinarily imagine, all the roads not taken existing alongside the ones we experience. The block is not broken by quantum mechanics. It is expanded into something like a branching tree, every branch fully real, every outcome realized somewhere in the structure. Other interpretations preserve the block in other ways, and the variety of them underscores how unsettled the matter is. There is a class of approaches developed to make quantum mechanics fully compatible with relativity's four-dimensional picture that treat the quantum state as spread across time as well as space, so that what happens at a measurement depends not only on the past, but partly on the future, on the conditions that will obtain when the measurement is complete. On these views, sometimes called retrocausal or time-symmetric interpretations, the future is not open, but rather participates in fixing the present exactly as the block would suggest, with past and future boundary conditions together, determining what occurs. These approaches remain minority positions, and they face technical challenges, but they exist, and they show that the four-dimensional block can be reconciled with quantum mechanics if one is willing to let the future have a hand in the present. In such pictures, the apparent randomness of measurement is not a sign that the future is unwritten. It is a sign that we have been looking at the situation from only one temporal direction, taking account of the past while ignoring the equally real constraints imposed by what is to come. The honest summary is that quantum mechanics neither confirms nor refutes the block universe, and anyone who claims otherwise is overstating the case. It depends on the resolution of the measurement problem, and that problem is genuinely open. If collapse is a real, fundamental, random physical event, then the block faces a serious challenge, and the future may indeed be open in a way relativity alone would not suggest. If collapse is not fundamental, if it is an appearance produced by branching, as many worlds holds, or by our neglect of future boundary conditions as the time-symmetric approaches propose, then the block survives, and the apparent openness of the quantum future is a misreading. Physics has not decided among these options. They make nearly identical predictions for the outcomes of experiments, which is precisely why the choice between them has remained unresolved for the better part of a century. The tension between the smooth determinism of relativity and the apparent randomness of quantum measurement is one of the deepest fault lines in all of physics, and where the block universe ultimately stands depends on how that tension is one day resolved. What can be said with confidence is that quantum mechanics does not straightforwardly demolish the block, as a first encounter with its randomness might suggest. The randomness that seems to open the future is inseparable from the unresolved question of what measurement really is, and several serious answers to that question leave the block fully standing, some even enlarging it. The four-dimensional structure remains a live possibility, consistent with everything we securely know, threatened only by one particular reading of a problem that physics has not yet settled. This leaves the block universe in a curious and telling position. It is not proven, but it is not refuted. It follows cleanly from relativity, sits in unresolved tension with one interpretation of quantum mechanics, and survives comfortably under others. Which raises the question that has hovered over this entire investigation without being directly confronted. If the block universe can be neither clearly proven nor clearly disproven by the physics we have, what is its actual standing as a description of reality, and what would it mean to live in a universe where time, in the deepest sense, does not pass at all? Consider first what kind of claim the block universe actually is, because its standing is easily misjudged in either direction. It is not a separate physical theory competing with relativity or quantum mechanics, making its own distinct predictions that could be checked against them in a laboratory. It is an interpretation, a claim about what our best physical theories mean, about the nature of the reality they describe. This places it in a peculiar epistemic position. The physics it rests on, the relativity of simultaneity, the four-dimensional geometry of spacetime, the entropy gradient that grains the structure, All of this is confirmed to extraordinary precision and is not in dispute. What is in dispute is what this confirmed physics tells us about whether time passes, and that question may not be answerable by any experiment, because every experiment takes place within time and produces its results in the form of measurements that the block and its rivals interpret differently while predicting identically. The disagreement is not about what we will observe, it is about what our observations mean. This does not make the question meaningless or merely verbal, a point worth insisting on against a certain dismissive attitude. Some argue that if two pictures predict exactly the same observations, the difference between them is empty, a matter of words rather than facts. But this is too quick. Whether the future already exists is not a trivial semantic question. It bears on whether the events of your life are permanent or fleeting, on what death removes and what it leaves untouched, on how to understand the relationship between the felt flow of your experience and the structure of the world that experience arises within. These are not idle distinctions. That an interpretation cannot be settled by a single decisive experiment does not mean it cannot be reasoned about, weighed against considerations of consistency, simplicity, and fit with the full body of what we know. The block universe earns its seriousness not from experimental proof, but from being the most natural reading of a theory we have every reason to trust, the reading that adds nothing to relativity and takes nothing away, that simply accepts the four-dimensional structure the mathematics presents without smuggling in a flowing present the equations never contained. Its principal rivals, by contrast, must work harder. To maintain that only the present is real, that the past has passed out of existence and the future has not yet come into it, one must find a way to reconcile this with the relativity of simultaneity, with the fact that different observers disagree about which events are present. If only the present exists, then whose present is it? The stationary observers or the walking observers, when they disagree by days about events in a distant galaxy? To privilege one is to reintroduce the absolute frame, the master clock, that relativity abolished. To accept both is to accept that the reality of an event depends on who is looking, which abandons the idea of a single shared reality. The presentist has responses to this and the debate continues, but the difficulty is real and it is severe. The block universe simply does not face it. By making all events equally real, it renders the disagreement about simultaneity harmless, a mere matter of how different observers slice a structure that contains everything anyway. The elegance of that resolution is a genuine consideration in its favor, even if it falls short of proof. Now turn to what it would mean if the block is real, for the things that matter most to us, because this is where an abstract question about the geometry of time touches ordinary human life. Begin with loss. Under presentism, when a moment passes, it is annihilated, gone utterly, its reality extinguished. When a person dies, they pass out of existence completely and are thereafter nowhere and nothing, their life a thing that once was and is no more. This is the picture of loss that seems to accompany the flowing view of time, and it is bleak in a specific way, the bleakness of total erasure. The block universe offers a strikingly different account. In the block, no moment is ever annihilated. Every moment exists permanently at its own location in the four-dimensional structure. A life that is ended is not erased. It remains complete at its place in the block. Every moment of it is real as it ever was. The person who has died has not passed into non-existence. They exist timelessly at their location in the structure, living their life, which is neither undone nor unmade by the fact that our own world line has carried us past the region where it occurs. This must be stated carefully, without overreaching, because it is easy to inflate into a consolation it does not quite provide. The block universe does not offer an afterlife. It does not suggest that the dead continue to experience anything beyond their lives, or that consciousness persists past death, or that we will be reunited with those we have lost. A life in the block is bounded, beginning at birth and ending at death, and within those bounds it contains exactly what it contained, no more. What the block offers is not continuation, but permanence. The moments of a life do not continue past their end, but they do not vanish either. They are eternally real at their place in the structure. The distinction is subtle but not empty. It is the difference between a life that once existed and now does not, and a life that exists timelessly at its own stretch of the block, forever having been lived. A childhood afternoon, a conversation, a moment of happiness is not obliterated by the passage of years. It sits permanently where it is in the four-dimensional whole, real, complete, safe from the erasure that the flowing view of time seems to impose. There is a well-known instance of someone drawing exactly this consolation from the physics, and it carries weight precisely because it came from one of the theory's architects. When Einstein's lifelong friend Michel Besso died, Einstein wrote to Besso's family, and in that letter he expressed the thought that the distinction between past, present, and future is only a persistent illusion. He was consoling a grieving family with the very implication we have been tracing, that his friend had not truly ceased to be, that in the deeper structure of reality, the moments of Besso's life remained as real as ever, and that death marked only the edge of a world line, not the annihilation of what that world line contained. Whether one finds genuine comfort in this is a personal matter, and it would be dishonest to insist that everyone must. The permanence the block offers is not the permanence most people long for when they grieve, which is continuation, presence, the return of what is gone. But it is not nothing. It reframes loss as separation across the dimension of time rather than obliteration, more like the way a distant friend, unreachable, still exists somewhere than like the way a snuffed flame simply ceases. Turn finally to what the block implies about living, about how one might hold this picture while going on with an ordinary human life, because a view of time that could not be lived with would be suspect on that ground alone. The most important thing to see is that the block universe changes nothing about the texture of experience and demands no change in how we conduct ourselves. You will still wake each morning to what feels like a new day. You will still deliberate over choices, strive toward goals, wait to learn how things turn out, feel the present as vividly present and the past as settled and the future as unknown. The block does not ask you to stop experiencing time as flowing, because the flowing, as we have seen, is built into the structure of any memory-bearing mind, generated afresh at every point along the world line. You cannot experience the block from outside all at once as a static whole. You are inside it, threaded along your own world line, encountering its moments in order, equipped at each with memories of the earlier ones and ignorance of the later ones. From that vantage, and it is the only vantage available to you, time will always feel like passing, no matter what you believe about its ultimate nature. What the block offers, then, is not a new way of experiencing time, but a new way of understanding the experience you already have, and perhaps a particular kind of composure within it. If every moment is permanent, then the moments of your own life have a reality that nothing can revoke. The good moments are not diminished by being over, because in the deepest sense, they are not over. They are fixed, real, eternally located at their place in the structure. This is a strange thought to hold alongside the ordinary business of living, and it does not resolve into simple comfort or simple unease. It sits as both at once. The universe, if the block is right, is not a story being told, unfolding moment by moment toward an unknown end. It is a completed structure, timeless and entire, in which the telling and the told exist together, in which every moment that has been or will be lived is laid out permanently in its place. And we are within it, small threaded world lines, experiencing our fixed stretch of the whole as a flowing present, encountering one after another the moments that have, in truth, always been there. Whether that structure ultimately reflects the nature of reality, or whether some deeper theory will one day restore the flow of time we feel so certain of, remains open. What the investigation reveals is that the passage of time, the most immediate and undoubted fact of our existence, is also among the most questionable, and that the universe described by our best physics may be one in which time, in the sense we mean when we say it moves forward, never moves at all.